In this lecture, we will introduce the symmetric matrices, namely reachability and controllability gradients, and will establish their relations to reachable and controllable subspaces. Okay, here is how we define those two matrices. Definition given two time instances, okay, T1 and T0. The reachability and controllability gradients for the linear system. X dot equals AX plus BU are defined or constructed as follows. Okay, so the reachability gradient, which is an n by n matrix, n being the dimension of our system, okay, or the size of our state vector. We are T0, T1. So this is a function of A and B matrices, or the system, and also this interval from T0 to T1. And it's constructed as this integral from T0 to T1, phi T1 tau b tau, and then what you do is you take the transpose of this term here, b transpose, and phi T1 tau transpose d tau. Okay, so this is the integrand is n by n matrix, therefore it produces an n by n matrix as the output. Moreover, because it's something times its transpose, the integrand is symmetric positive semi-definite. Therefore, the output, the reachability gradient, that matrix is also positive, symmetric positive semi-definite. Okay. And this is the controllability gradient. This is how it's defined. T0 to T1, phi T0 tau b tau transpose, and then you take the transpose of this matrix. By the way, this is our state transition matrix phi. T0 tau transpose d tau. Okay. Again, it's symmetric, positive, semi-definite matrix. Now, let's establish the relations of these two symmetric, positive, semi-definite matrices with the reachability and controllability, or reachable and controllable subspaces of our LTB system. And this is the theorem that we will prove in this lecture. So suppose that we've given two time instants, T1 and T0. We have that the reachable subspace is equal to the range space of reachability gradient T0, T1. Okay. Oh, so let's remember what reachable subspace was. So what you do is you're given a system and you're given an interval from t0 to t1. You set the initial condition to the origin, okay, and then you apply inputs through this interval t0 to t1 and run the system, and then you go and check the position of the state at t equals t1. Okay, so whatever state that you reach with that input that you apply, that is part of your reachable set. And then you go and pick another input in principle. Again, you start from the origin, and that input will take you somewhere else, and that somewhere else, that final state is also an element of your reachable subspace. So you go that, you keep doing that for all input functions that are applied to the system on this interval t0, t1, and instead of all those final points that the state reaches at the end of the interval at t equals t1, those points make your reachable set, and that set can be shown easily to be a subspace. Therefore we call it the reachable subspace for this system for the given interval t0 to t1. And now this theorem claims that that reachable subspace, the set of all points that we can reach from the origin in the interval t0 to t1, must be equal to the range space of that matrix, symmetric positive semi-definite matrix that we constructed here through this integration. Moreover, okay, we continue with the statement of our theorem. If x1 belongs to range space of the Gramian, okay, so that means if x1 belongs to the range space of this matrix, so that means we can find a vector that's called eta1 such that this matrix times eta1 equals x1. So that's the definition of the very definition of range space. Okay, with x1 given as the Gramian t0 t1 times eta1. Okay, so here eta1 is a vector in Rn. Okay. And x1 is a vector in Rn, and n is the order of our system. And also this matrix is n by n. Then the control input u of t equals b t transpose phi t1 t transpose eta1. Okay, turns out to steer the state from the origin to x1 at the end of the time, or the interval t0 t1. For t in this interval can be used to transfer the state from the origin at the initial time, okay, from x t0 equals 0 to x t1 equals x1. Okay, so that's also important. So that means if you have computed the reachability Gramian, okay, if you have that matrix, and note that it's a constant matrix. Once you compute that integration, it's a constant matrix. If you have that matrix, then you can use that matrix to compute or to generate control inputs, okay, that would take your state from the origin to the desired final position. And for that, all you have to do is you have to figure out this eta 1, which would be easy because it's just a constant matrix, for a given x1. Okay, provided that x1 belongs to the range space, and x1, whenever x1 belongs to that range space, automatically, this is what we're going to prove, x1 also belongs to the reachable subspace, okay, of the system. Okay, so this is not at all an obvious result, and the proof is interesting, I think, and it's quite elegant. So therefore, let's go through the steps, and it's not very long. Okay, so here is the proof, and what we're trying to prove is, I'm talking about this statement. Here we have a subspace. Range of some matrix is also subspace. So we're trying to prove two subspaces of Rn to be equal. Okay, so whenever you want to prove that two sets are equal to one another, a general way to do that is first you show one is the subset of the other, and then you show the other is subset of the first one. And if both are subsets of each other, then it means that they must be the same set, the same subspace. So, therefore, in part 1, we're going to prove that the range space of the Gramian VR, WR, T0, T1 is a subset of the reachable subspace of the system. Okay, so let's therefore try to establish that subset relation. And how you prove that some set is a subset of the other? What you do is you pick an arbitrary element from the set, the subset set, and then you show that that arbitrary element is always also an element of the other set, and so that would guarantee that this set is a subset of the one on the right. Okay. So, therefore, we begin by picking an arbitrary element from the range space of the Gramian. Okay. Let x1 belongs to range space of the reachability Gramian. Okay, WR. Then, by definition, there must exist a vector, okay, eta 1, we call it in Rn, such that x1 equals WR times eta 1. Okay, this is exactly what this range space business means. Now, we start the system from the origin. Okay, so initially xt0 equals 0, and let's pick the input to equal bt transpose state transition matrix T1 T transpose times eta 1. And let's see where this input takes the state from the origin to at the end of the interval T0, T1. Okay, so let's figure out what x of T1 is if you drive the system with this input, where eta 1 is coming from this x1 W1 WR eta 1 relation, since we picked, and we can find such eta 1 because we picked x1 that belongs to the range space of our Gramian. Okay, all we have to do is we put this input expression into the solution expression, which contains the state transition matrix and the integral. So let's do that. This imply what? Let's see what it implies. X of T1 equals. Now, solution x of t equals what? The state transition matrix times the initial condition plus we have the integral term. Now, since the initial condition is chosen to be 0, so we're starting from the origin, we only have on the left-hand side the integral, okay? From the initial time to final time. State transition matrix T1 tau b tau u tau d tau. So this is x of t1 for any input u of t starting from the initial condition x t0 equals 0. Okay. Now let's see what happens to x of t1 if we pick this input, this expression given in terms of eta 1. So let's do that. So that equals from t0 to t1 phi t1 tau b tau, and then this is our u of t. Therefore u of tau is b transpose tau phi t1 tau transpose eta 1 times d tau. Okay, so that equals what? This can be written as, since eta 1 is just a constant vector, this can be written as this whole thing times eta 1. And we immediately realize that this whole thing is our reachability gradient. So that equals WR T0 to T1 eta 1. And this equals, okay, that equals x1 because eta 1 is chosen using that relation in the first place, okay? And that equals x1, and by definition, since we were able to find an input, okay, u of t, such that we reached, starting from the origin, we reached x1 at the end of the interval. This x1 must be part of the reachable subspace, okay? So hence x1 belongs to the reachable subspace. And now since x1 was an arbitrary element of the range space of the Gramian, reachability Gramian, so that means no matter what element you pick from the range space of the Gramian, that will always belong to the reachable subspace. And as a result, we have proven that the range space of the Gramian is always a subset of the reachable subspace, R T0, T1. Okay, so that completes part 1. Since that completes part 1, and also that completes this second part of the statement that starts with moreover. Okay, if you have the Gramian, then by choosing the input defined through that eta 1, where eta 1 is such that x1 equals the Gramian times eta 1, x1 is where you want to end up at, you can always steer the state to the desired final position. So the second part of the theorem is also proven. Okay, well, by second part I mean the second statement. We still have part 2 to prove, okay, so the reverse direction. So let's do that. Okay, so let's prove part 2. Okay, reachable subspace is a subset of the range space of the reachability Gramian. So let's try to prove this. Okay, so this time we're going to do the same thing, okay? That is, we will start with an arbitrary point from the reachable subspace, and we're going to show that that arbitrary point must also be an element of the range space of the Gramian, and that will establish what we want to establish. So let therefore x1 be an arbitrary vector from the reachable subspace. Then, by definition of reachable subspace, we can find some input function u of t to be applied through this interval from t0 to t1, such that x1 equals okay, remember that we start when we talk about reachable subspace, the starting point is always the origin. Therefore, x1 equals just the integral term from t0 to t1 phi t1 tau b tau u tau d tau. Okay. Now, let's choose an arbitrary eta1 that belongs to the null space of the reachability Gramian. Okay, null space of W of R. Okay, that is W of R times eta1 equals 0. Now, what does that have to do with x1? Now, we're going to see what. Okay, now then we can proceed as follows. 0 equals W of R times eta1, because eta1 is an arbitrary vector that belongs to the null space of the Gramian W of R. If that's 0, clearly, if you multiply that by eta1 transpose from left, that's still a 0. This time, this 0 is a scalar 0. Okay. Now that equals from t0 to t1. Okay. eta1 transpose phi t1 tau b tau transpose phi t1 tau transpose eta1 d tau. Okay, so what we did here is the following. Forget about these eta1 transpose and eta1. Just consider this integral. And that integral is clearly, by definition, the reachability Gramian. Okay, W of R. Now, what we do is we multiply W of R with eta1 transpose and eta1 from left and right, respectively. Since these are constant matrices, we can easily carry them inside the integration. And when you do that, this is what you obtain. Okay. Now, and this thing is, this integral is 0. Now, because of the special structure of the reachability Gramian, namely its symmetric nature, this thing here, the integrand, can be written as something transpose times itself. And that can be written as the norm square of that something. Okay, so therefore we can write or rewrite this as b tau transpose phi t1 tau transpose eta1 norm square, and then we're integrating that d tau. Okay. Now, since the integrand is norm square, it's never negative, and then you're integrating something that's non-negative, and the left-hand side is 0, you obtain 0, therefore the integrand must be identically 0, okay, at least for well-behaving functions. So that implies that bt transpose, that implies that this norm square is 0, okay, through this interval from t0 to t1. That means the norm is 0, and that means the thing that's being normed must be 0. So what's inside the norm is bt transpose phi t1 t eta 1. Okay, this is identically 0 for all times in the interval from t0 to t1. Okay. Okay, here is the critical step. Therefore, we can write now the following. x1 transpose times eta 1 equals, okay, from t0 to t1. x1 is here. Where is it? x1 is here, okay. Now what we're doing is we're transposing it and multiplying it with eta 1. Now transposing it simply means the same integral, but, well, again we have the integral, but this time the integrand is transposed, and we're multiplying that integral by eta 1. Eta 1 is a constant vector, therefore we can carry it inside the integration. And if you do that, this is what you have. U transpose B transpose and phi T1 tau transpose eta 1 eta. Okay, so this transposed terms are coming from the expression for x1, and then we have this eta 1 here, like our constant vector. Now, here I forgot a transpose. Okay, now this expression is 0 for all times. Okay, that belongs to that interval from t0 to t1. Therefore, this thing here equals 0. So regardless of the input, therefore, this inner product produces 0 outcome. Okay, therefore that equals 0. Now, which implies that this vector and that vector, they are orthogonal to one another. x1 is orthogonal to eta 1. Now, since eta 1, which we picked arbitrarily from the null space of the reachability gradient W of R, and likewise x1, that's coming from the reachable subspace, and x1 t0 to t1 was also arbitrary. Okay, arbitrary. We have the following. Okay, so once again, pick any x1 from this subspace and pick any eta 1 from that subspace, and those two vectors are always produce 0 inner product. They're always orthogonal. So that means the subspaces themselves must be orthogonal to one another. Range space of reachable subspace, reachable subspace must be orthogonal to the null space of the reachability gradient. Okay. Okay, so we have x1 that belongs to null space of this vector orthogonal complement. Okay. Okay, so x1, therefore, since since eta 1 belongs to the null space of reachability gradient, and x1 is always orthogonal to eta 1, so that means x1 must belong to the orthogonal complement of that subspace, null space of W of R. And from 541, we remember that null space of a matrix's orthogonal complement equals the range space of that matrix's transpose. So that equals range space of W of R transpose. Now, the nice thing about the gramians is that they're symmetric Okay, and because of the symmetry, this transpose can be removed. In other words, here we have range space of W of R, because W of R and W of R transpose, they are the same thing. Okay, so that completes, therefore, the proof. So we picked an arbitrary x1 from the reachability subspace, and we have shown that that x1 must necessarily belong to the range space of the reachability Gramian. Okay, therefore this subspace is a superset of this subspace, and that was what we were trying to achieve. In the first part, we have shown the reverse direction. Therefore, these two subspaces must be the same subspaces. They are equal to one another. Okay, now let's also talk about the controllable subspace and controllability Gramian. The proof is very similar to what we have established here. Therefore, it's left as an exercise for those of you who have time and interest. Okay. So this is the sister theorem. Given 2 times, okay, 2 instants, T1 and T0, we have the following relation between the controllable subspace and controllability Gramian. Controllable subspace equals this subspace, which is the range space of the controllability Gramian. T0, T1. Remember what controllability subspace or the controllable subspace was. It's in a sense defined in a reverse fashion to reachable subspace. We start from arbitrary initial conditions, and then for each of those initial conditions we try to figure out an input. Okay, and through that input we want to end up at the origin at t equals t1 at the end of our interval. If we can do that, if we can find such an input, then our starting point is an element of the controllable subspace, and then you do that all the points in Rn, and whenever a point can be driven to the origin, then that point is it belongs to your controllable subspace, and the set of all those points make this set. Okay, and this theorem now claims that that subspace can easily be computed using the controllability Gramian. Moreover, if the initial condition is picked from the range space of the controllability Gramian, which by definition of range space implies that we can find an eta 0 such that x0 equals controllability Gramian, the matrix, times that vector eta 0. Then the control input u of t chosen as phi t0t transpose times that vector eta 0 applied for the interval from t0 to t1 can be used to derive the state from the initial condition x0 to the origin, to transfer the state from x t0 equals x0 to the origin.